Accurate and interpretable air pollution forecasting is not just a technical challenge, it's a public health imperative. In cities like Stockholm, where air quality directly impacts millions, timely predictions can mean the difference between issuing life-saving warnings and missing critical windows for intervention. But here's the paradox. Models that are highly accurate often operate as black boxes. Meanwhile, models that claim to be interpretable sacrifice performance. This trade-off has long held back real-world adoption in operational environmental management. Our new research, accepted at the 2025 IEEE International Conference on Big Data, introduces a breakthrough framework, physics-guided spatiotemporal decoupling, a model that doesn't just predict air pollution better, but explains how it does so. At its core, the model decouples the complex spatiotemporal evolution of pollutants into two transparent, additive components, each rooted in physical reality. The first component models spatial transport, specifically advection, the movement of pollutants driven by wind. Unlike traditional models that use static or correlation-based graphs, our approach builds a dynamic, wind-conditioned transport kernel. The weights between stations aren't fixed. They're learned, and they change in real time based on wind speed and direction. If the wind shifts from south to west, the influence of upwind sources updates instantly. This isn't just a pattern, it's physics in motion. The second component captures local dynamics, the site-specific processes like emissions, chemical reactions, and local mixing. We use a novel variant of interpretable attention, where each forecast is traced back to specific historical inputs, past PM₁ levels, temperature, precipitation, even calendar features like weekdays or holidays. This isn't just theory. We tested the model on a comprehensive dataset from 9 monitoring stations across Stockholm, spanning over 4 years of hourly measurements. The results? Our model consistently outperforms state-of-the-art baselines in both MAE and MSC across 24, 48, and 72-hour forecasts. But the real win isn't just accuracy, it's interpretability. Take a 72-hour forecast at St. Eriksgaten, a central station. The model shows that during southeasterly winds, the dominant influence comes from Hornskatten and Torkel-Knutsenskatten, upwind stations. When the wind shifts to the southwest, the model dynamically reassigns over 90% of the transport contribution to Lilla Essingen. And critically, this aligns perfectly with observed meteorological data. This isn't hindsight. It's real-time, physics-consistent attribution. We also visualize the attention mechanism. Color-coded heat maps show how past pressure, precipitation, and PM₁ levels contribute to future forecasts. The influence decays smoothly over time, reflecting the diminishing relevance of older data, just as physics would predict. So what makes this framework fundamentally different? First, it's interpretable by design. Every component has clear physical meaning. The transport module reflects advection. The attention module reveals temporal dependencies. No hidden layers obscure the logic. Second, it's physically grounded. The model doesn't just mimic real-world behavior, it learns to emulate it. The adjacency scores are shaped by wind alignment, distance penalties, and even a learnable residual matrix to account for fixed geographical barriers. Third, it's scalable and efficient. Unlike physics-informed neural networks that require iterative solvers or hybrid models tied to expensive numerical simulators, our model trains end-to-end on a single GPU. No external simulators. No heavy computational overhead. And finally, it's actionable. Municipal authorities don't just need predictions, they need understandable ones. When a pollution spike is predicted, they need to know, is this due to local traffic? Is it being blown in from a nearby industrial zone? Our model answers both questions, spatially, temporally, and causally. In a world where AI is increasingly used to guide high-stakes decisions, this is more than just a technical improvement. It's a shift toward trustworthy, transparent, and responsible AI. By combining deep learning with physical principles, we've built a model that doesn't just forecast air quality, it explains it. This is not the future of air quality prediction. It's the present. And it's time we started listening to the data, not just what it says, but how it says it.